Class, welcome to our lectures on quantum field theory, and this is chapter 3, Introduction to Group Theory. And again, I'd like to recommend to you the book of Michio Kaku, Quantum Field Theory, F. Mandel and G. Shaw, Quantum Field Theory, F. Ross, Relativistic Quantum Mechanics and Field Theory, as the books you can read along this lecture. So, an abstract branch of mathematics called group theory plays a very important role in modern particle physics. The reason is that it's because group theory is related to symmetry. For example, an important group in physics is the rotation group, and it is related to the fact the laws of physics don't change if you rotate your frame of reference. In general, what we are after is a set of equations or laws of physics that keep the same mathematical form under various transformations. So to start with, we will define what is a group. A group G is a set of elements A, B, C, which includes a multiplication or composition in general, composition rule such that A as an element of G and B as an element of G, then the product is also a member of the group. That is the closure property. That is, if you make a composition rule of A and B, you find it also in G. This means that actually the composition rule is not, this is not the literal multiplication, but the multiplication is just an operation that you do with the elements. It's multiplication B, or composition rule could be addition, the ordinary multiplication, division, or operations that you can think of for a group. If AB is equal to BA, then the group is abelian. We should remember this. And if AB is not equal to BA, then the group is non-abelian. The actual implementation of multiplication or composition rule can vary from group to group. So you don't really say that a group is the same as the other group, because sometimes the composition rule, the multiplication operator in that group is different. Or say, for example, your first group would have a composition rule of addition, and the other group would have a composition rule of multiplication. A group G must satisfy four actions given A, B, C element of G. So if you have this property of a group, then that group is associative. And this one is the existence of identity E, such that when you multiply an element of the group, it gives you the element. So in this case, you have A times E, or the identity is equal to E times A equals A. And also the existence of the inverse, such that when you multiply A and its inverse, denoted by A to the negative 1 or A to the minus 1, and this one is equal to A to the minus 1 times A, and that should equate to the identity. And the number of elements in a group is the order of the group. So if your group has only 3 elements, then the order of the group is 3. And if the group has an element that goes to infinity, then the order of the group is infinite. Now we will go to group representations. So if we denote a group representation by F, this means that you have different set of elements in this group. So for example, if you have a representation mapping that takes group elements G, element of G, into linear operators F that preserve the composition rule of the group. Say for example, this G is just an example, may be just pure numbers, and the linear operators F in a group representation could be functions, for example. So if the composition rule of the group is preserved, so in G, for example, if A if A in G times B in G is equal to of course this is sorry so if you have A in G and B in G, or element of G, then your AB is also an element of G. So in the representation, the group representation would be, if you have F of A times F of B, then it would have to be equal to F of A B. And also this representation group also preserves the identity here. So if you're E, of course the identity E, the identity is an element of G, so your F of E, which could be a matrix or a function, is an element of the representation group of F. Say for example it's F prime. Now suppose that A and B, element of G, and F element of H, where H is some other group. So you have to remember the definition of the group. So if the composition rule satisfies this one, then G is homomorphic. This means that the structure is similar to H. So example, the set of all integers form a group under addition. So this is the solution. The set of all integers form a group under addition. Taking the composition rule to be addition, you let Z1 as an element of Z, and then you have Z2 as an element of Z. So clearly you have Z1 plus Z2 is also an element of Z. It would be another integer. So if you add two integers, it also gives you an integer. So it's also an element of Z. So therefore, it is a group. And does the identity exist? So say for example, your identity is equal to 0, e. So if you add e, or if you add 0 to an integer, what gives that addition? It gives the same integer. So this one, and as you can see, it's also a commutative group. It also gives you z for any z in the big Z. So it's always an integer. So addition is commutative for integers, and so you can call that group abelian. The inverse of z is just negative z, because it gives you the identity. So in this case you have negative z, so you have z plus negative z is equal to e, which is equal to 0, and so it satisfies this property. So it is a group. The next example is this: the set of all integers form a group under multiplication. The set of integers does not form a group under multiplication. If you take z1 and z2 elements of z, clearly that the product is also in z, because the product of two integers is an integer. But the problem here is that you have no inverse for each element, since the inverse is 1 over z, which is a fraction and it's not an integer. So you have this one therefore is not a group under multiplication, but under addition it is a group. The group also has parameters. So for example, an ordinary functional position is specified when an input x, for example, y is equal to f of x. Analogously, a group can also be a function of one or more inputs called parameters. So let a group G be such that individual elements G of small g, element of G are specified by a finite set of n parameters. If the set of parameters are denoted by theta 1, theta 2 up to theta n, then the group element is then written as G equal to G of theta 1, theta 2 until theta n. And also here in this case, the identity element is where the parameters are all set to 0. So you have E equal to G 0, 0, 0, 0, 0, and so on. So we now go to Lie groups. There are discrete groups with a finite number of elements, but most of the groups have an infinite number of elements, but still have a finite set of continuously varying parameters. So if a group G depends on a finite set of continuous parameters theta I and derivatives of the group elements with respect to all the parameters exist. The group is called a Lie group. So let's check what is a Lie group. So begin with a group with a single parameter theta. For example, just theta as our parameter. Obtain the identity by identity element by setting theta is equal to 0. So this is your identity element of the group. By taking derivatives with respect to the parameters and evaluating the derivative at theta is equal to 0, we obtain the generators of the group. So if we denote the abstract generator by x, then x would have to be in this form. In general, for n parameters of a group, then there will be also n generators of that group, and each generator is given by this one. Rotations have a special property. They are length preserving. So if you rotate a vector, it maintains its length all the time. A rotation by negative theta undergoes a rotation by theta as well. Hence, rotations have an orthogonal or unitary representation. In quantum field theory, a unitary representation of a group or of the group with Hermitian generators xi is of special interest. In this case, our generators is of the form of this form, I mean. So you have the presence of this factor negative I which is equal to square root of negative 1. In comparison to 3.4, you don't have this factor here. For some finite theta, the generators help define the representation of the group. So if we consider a small real number epsilon greater than 0 and use a Taylor expansion to form a representation of the group denoted by D, for example, and that will just be that one. So if theta is equal to 0, then clearly the representation gives the identity. So we have, if we recall, this is the expansion of the exponential function. So your e to the ix will just be equal to 1 plus, or your e to the, let's see, your e to the ix will just be equal to 1 plus ix plus 1 over 2 factorial negative 1. So this would be negative x squared plus I cube would be just negative I cube would just be negative I, so you will have negative I 1 over 3 factorial x cubed. Then you will have plus 1 over 4 factorial x to the fourth, and so on for your e to the ix. So the representation of the group can be defined in terms of the exponential using this one, this definition. So say e to the theta x. So here, if you have x as Hermitian, which means that the adjoint of x is the same as x, the representation of the group is unitary, since you have this one here, and that if you multiply d adjoint d, then that will just be equal to the identity. One reason that the generators of a group are important is that they form a vector space, which means that two generators of the group can be added together to obtain the third generator. And generators can be multiplied by a scalar and still have a generator of the group. A complete vector space can be used as a basis for representing other vector spaces. Hence, the generators of a group can be used to represent other vector spaces. So, as an illustration, we have the Pauli matrices from quantum mechanics, and these can be used to describe any 2x2 matrix. And this will be studied in the following slides later on. The generators satisfy a commutation relation, and which is this one. Here you have the structure constants of the group, which is represented by Fi of ijk. And by the way, 3.7, this commutation relation, is called the Lie algebra of the group. And now let's go to an important group in particle physics, which is the rotation group. The rotation group is the set of all rotations about the origin. Rotations should preserve the lengths of the vector, which means that the matrices are, in this case, unitary. It is clear that the set of rotations forms a group, because, say for example, you have rotation R1 and R2. The combination or the composition rules of these rotations should be a member of the group. So say for example, rotation R3 is done by doing R1 and then doing R1 and then followed by R2. This could be done by just one single rotation of R3, for example. So as the composition rule said that if A is an element of G and B is an element of G, then AB is also an element of G. Hence R here is a member of the rotation group. So let's look at the figure here. Two rotations in sequence are the same as a single rotation that is the sum of two angles. So you have here a single rotation theta 1 and then a single rotation theta 2. The sum would be a single rotation of theta 1 plus theta 2. In general, however, doing one rotation and the next is not the same as doing the second rotation first and then followed by the first rotation. So this is not equal in general. So to be able to prove this, you can put a book on the table, then rotate it about two different axes, and then try the experiment again, doing the same rotations but in different order. The end result are not the same. So say for example, if you rotate, if you have a book that's let's do this. So if we have a book here R and we rotate this on the x-axis, for example, say let's rotate this on the x-axis, and this would just look like the that one. And then if we rotate on the say for example z-axis, and this would just be, this would just look like that. And the z-axis, this will just be that one. So let's look at the other rotation on the z-axis, for example. Doing the z-axis first, we have from here we have that one, and then on the x-axis we have this. So it's different. So this is rotation on the x, and then on the z, and then this is rotation on the z and then on the x. So it's not the same. So in this case, the rotation group is non-abelian. However, the rotations are associative. The rotation group has an identity element, and this is simply doing no rotations at all. And the inverse of a rotation is simply the rotation carried out in the opposite direction. These are very important things for the rotation group: the identity and the inverse. So let's now going to represent rotations. Let xi be the coordinates of a two-dimensional vector, and let xi prime be the coordinates of the vector rotated by an angle theta in the plane. The components of the two vectors are related by the transformation as this one here, where rij are elements of a rotation matrix. And this is now the representation of the rotation group. That is a matrix with elements rij. So specifically, if you remember um, lectures in vectors, you encounter this one, and your rotation uh, representation is just given by this matrix here. So that your x1 prime would be this, and your x2 prime would be this one. So you can write the rotation matrix if you decompose this, if you decompose these two equations here into this one. By decomposing, I mean that you separate this vector x1, x2, rewriting it in terms of matrix to x1 prime and x2 prime. So the transpose of the rotation matrix is actually just equal to this one, and the transpose is just equal to the inverse if you would compute. I mean, the transpose times the original matrix will just be equal to the identity matrix. Here. That's the transpose in this case is equal to the inverse of the original matrix. So if you would recall, sine of negative theta is just equal to negative sine theta, and cosine of negative theta is just equal to cosine theta. So your transpose is just equal to r of negative theta. In that case, that is the inverse. So that should be equal to the identity matrix. In group theory, groups are classified according to the determinants of the matrices that represents the group. For this case, for this particular case that we're studying, the determinant of r theta is equal to 1. And if the determinant is equal to 1, then the rotation matrix corresponds to a proper rotation. So we will make a subscript 1 of r as a rotation of theta 1. So if the determinant of r1 and the determinant of r2, then the product is unity, of course. And the product of two rotations also has an inverse, which is this one. So if you have two successive rotations r1 and r2 taken together, they form element r3. So we're just talking about determinant of r equal to 1. So as before, the transpose is the inverse here, and in terms of the components, you have here RT could also be written as R2 inverse and R1 inverse. Thus, you will have the representation matrix, or uh, matrix representation preserving the properties of the rotation group. So let's now go to a special orthonormal matrix. Call that SON. That is, the N here means that your matrix is N by N. SON is an important group in particle physics. The group SON are special orthogonal N by N matrices. These matrices have determinant equal to 1, and SON is just a subgroup of ON, which are orthogonal N by N matrix that can have arbitrary determinant. Rotations can be represented by orthogonal matrices which themselves form a group. The SO3 is a representation of rotations in 3 dimensions. And the group consists of 3 by 3 orthogonal matrices with determinant 1. So, looking at the matrix O, the transpose OT is the inverse. So you have I call this by the way, I call OT as the transpose of O. A special orthogonal matrix is one with positive unit determinant here equal to 1. And SO3 group has 3 parameters, 3 angles, eta, phi, and theta, defining corresponding rotations about x, y, and z axis. Then you would have this. The matrices are representing rotations in 3 dimensions. This is for the rotations in the x-axis, rotations on the y-axis, and rotations on the z-axis. So as you can see, these are jumbled sine, cosines, and 1. So the elements are just 1, cosine, sine, and zeros. So rotations in 3 dimensions, or even more, do not commute in general. So in this case, we have already encountered this. So you have RK, RP is not really equal to RP, RK, so they don't commute. So if we start with Rx of eta, if we get the derivative of it, which is this one, and then letting eta to 0, we obtain the generator, this one here. This is the one of the generator of the group, one of the generators of the group. And then if you do the same for x and for y and z axis, evaluating phi equal to 0 and theta equal to 0, we get the other 2 respective generators of the group SO3. So these are the matrices, the important matrices that generates SO3. These matrices are the angular momentum operators, and they are generators of rotation. They can build infinitesimal rotations. For example, an infinitesimal rotation about the z-axis is by an angle epsilon theta, where E is a very small positive parameter, is written as this one. So the algebra of the group is just a commutation relation satisfied by the angular momentum operators. This is the Lie algebra of the group. For that Lie algebra, the structure constants epsilon ijk is in that case is just the Levi-Civita tensor, which takes on values of +1, -1, and 0 according to these rules here given by 3.16. So if you have a cyclic permutation of 1, 1, 2, 3, then you will have values of +1, and for anti-cyclic permutation like 1, 3, 2, 3, 2, 1, 2, 1, 3, you have -1 as values, and other combinations with repeated indices is 0. So now we'll go to an example. Show that the representation of the rotation group is of the form exponential of I jy phi. Now we have to show that ry of phi is just equal to exponential of exponential to I jy phi. So recalling that your exponential of I theta is cosine theta plus I sine theta, then noting that your exponential of x is given by this expansion, so we can extract the sine and cosine functions as your cosine given by the sum of the even powers of theta, and your sine theta will just be the sum of odd powers of theta. But in that case, you have alternating positive and negative coefficients. Now your exponential of I jy theta would have to be written in this form. What are the powers of jy matrix? So calculation would show that jyn takes one of two values depending upon whether n is odd or even. So jy1, jy3, jy5 would have this, and for even powers you have this one. Now the expansion becomes, in terms of matrices, would have to look like this. And so if you would combine them element by corresponding elements, then you would have this one. Finally, this is ry of phi. So if you would do the same for rx and rz, then this would just be this one. This one is exponential to ijz theta x. I mean theta, sorry. Again, our z theta is written as e to the I j z theta. A rotation about an arbitrary axis defined by unit vector n is given by this one. It's a combination of the three directions of rotation. So this is just given by this one here. Orthogonal transformation preserve the lengths of the vectors. So the length of a vector is invariant under rotation. Invariant. That means it's the same whatever rotation you do. This means that given a vector x with length like that, x squared plus y squared plus z squared, when transformed under rotation x prime gives when transformed under rotation x prime equals rx gives the same thing, the same length. So this is it for this session. We will proceed with the second part of this chapter, and we'll be starting with the unitary groups.